SwayamPrabha. Digital India. Educated India.
Welcome back. In the last lecture, we were discussing the entropy change, particularly for pure substance, incompressible substances and ideal gases. And as well as we looked at idealized processes called asentropic process. Okay, and particularly we developed the property relation for these processes. So in this particular lecture, we'll start with the derivation of a reversible steady flow work relation. So let me start with a basic energy balance, particularly for reversible process. Okay, so we are assuming this to be a positive value here, del Q reversible minus del W reversible, and that will be for the steady flow conditions. You have change enthalpy or in terms of differential function or in terms of dH plus dK plus dP. Okay. Now for the case of a reversible process, we can consider this to be your TdS, and in the previous lecture we have derived that TdS relation in terms of enthalpy, and then we can write this as dH minus VdP. Okay. So now we can express this energy balance now in terms of dH minus VdP minus del W reversible, that is going to be dH plus dK plus dP. Okay. So this can get cancelled, and what we have is del W reversible as VdP plus dK plus dP. Okay. So if we assume the changes in the kinetic energy and changes in the potential energy to be 0, then we can write this as minus VdP. Okay. If you include the changes in the Ke, then you have to also include these terms. Okay. Now this is the amount of work out from the system or to the work done on the surrounding. So if you consider this negative, as this work has to be done on the system, then this can be written as W reversible in, that is input work. This can be written as simply VdP. Okay, considering your delta P delta K to be 0. Okay. So it's very clear that if you have a larger surface volume, you will have this term, that is the work consumed is going to be greater. Now in case of steady state involving no work interaction, you can rewrite this expression in the following form. If you are considering incompressible fluid, then this is going to be P2 P1 plus V2 square V1 square by 2, the kinetic energy term, plus G Z2 minus Z1. Okay. So this is for incompressible fluid, and since W work is going to be 0, or if you integrate here, this should be also integral of this. So this could be written as W reversible in as simply VdP. Okay. So when this is 0, you and the other terms are not 0, let us say del K and del P, then you can write this expression in this form. This is equal to 0, and this is nothing but Bernoulli's equation. Okay. Now you can clearly see there is a two different expression for the work related to the open system, where we have clearly written in terms of VdP, that is what we derived here, and for the case of a closed system is going to be PdV. Okay. So you have a summary where we have said that for a steady flow system, so you have W reversible in terms of minus integral of VdP. Okay. So here indicates is out, negative indicates that you are doing the work on the system, and this is the case for the closed system. Okay. Now we can try to calculate this work reversible for two specific systems. One is for the liquid, saturated liquid, and other is for the saturated gas. Okay. So here is an example where you have both this process which we are going to consider is asentropic process, that means the entropy is constant, and then we are going to analyze how we should be considering the calculation of W reversible in. Okay, considering in the negative I have already absorbed by taking the direction, changing the direction from the out to the in, and thus I can write this expression, the work reversible in, as simply VdP, okay, which is going to be for the compressible case, that is case A, okay, which is this, as simply V P2 minus P1, okay, and V here is going to be V1, which is going to be Vf at, that is fluid at 100 kilopascal, okay. What about B? B is your gas. Now here of course we need to know the relation between V and dP, because V is not constant, okay, and in this particular case we are going to make use of the TdS relation in terms of enthalpy. Considering this is an asentropic process, this is going to be 0, thus your VdP is nothing but dH, and therefore we can write W reversible in simply as integral of dH from 1 to 2 for the case of B, and that will be your H2 minus H1. Okay. This was the case where you had two cases, one for the compressing liquid and the other case was the gas, where the compressing vapor inlet and outlet pressure were same as that for the compressing liquid, but the expressions are quite different, the values are going to be extremely different as well. Okay. Now let us look at the case, and we have discussed this aspect earlier also, that the steady flow devices deliver the most and consumes the least when you consider the process reversible. So we have looked in this particular aspect when we are discussing about your boundary work, okay, and here we can now derive it very rigorously. Okay. So you have a turbine where the inlet pressure and temperatures are given, and what we want to derive is that the reversible turbine work is more than the actual turbine, more than or equal to that of the actual turbine, and inlet and outlet condition for the as well for the reversible as well as for the actual turbine would be considered to be same. So let us take a simple analysis of the energy balance. We will consider again Ke P to be 0, okay, changes in the Ke and Pe. Start with basic energy balance here. That means your, for the steady flow devices, this is going to be del W actual is equal to dH, okay, and similarly you can write for the reversible process here, okay. Now this is going to be same because H is a state function, that is a property, and hence it depends only on the initial and the final condition, the changes in the enthalpy. So you can write this expression, that means this left hand side should be same, which essentially means I can write as follows, okay. You can rearrange, bring this W together, so this is brought here and this is brought there, minus del Q actual, okay. Now del of Q for the reversible case is nothing but TdS, okay, and we know that ds is equal to del Q by reversible by T, but for the actual case this ds would be del Q by T, which means your ds is greater than or equal to the ratio of your Q by T for the actual system, and thus this expression is going to be greater than or equal to 0, okay. So this clearly implies that your W the reversible is greater than or equal to for the case of actual, okay. So this is how we can conclude that a reversible turbine delivers more work than that of irreversible one if both the devices operate between the same endpoints. That means your P1 T1 and P2 T2 are same for the both the devices, okay. So we summarize here as follows, that the work producing device such as your turbine deliver more work, and work consuming devices such as pump and compressor require less work when they operate reversibly. This is something which we can now conclude here, okay, based on this analysis. Now this here of course we have considered for the case of positive value of your work, and essentially this is a work producing condition. That means this particular derivation was for the case of work producing device, and you can do the same exercise for work consuming device as well. Okay, so let me just describe the compressor work, and here the compressor, again we can write this compressor work in this form. Okay, the in stand for the work needed by the compressor, and this can be written as VdP, assuming of course your kinetic energy and potential energy to be same. Now you can operate the compressor at different conditions. You can operate at constant temperature, you can operate at adiabatic condition, or you can operate at isentropic condition as well. So that means you can have different relation between V and P, and based on that your work required would be different. And this is summary of the derivation. So this is the case when we have considered isentropic. We have already looked into this, that for adiabatic reversible case the polytropic expression N turns out to be K, and this becomes your PV to the power K is equal to constant. This essentially means that entropy is constant, and for that this is the expression for the work compressor. Okay, and you can write in the general polytropic PV to the power N. Okay, so where basically nothing but K in this expression is turned out to be N here. Okay, and for the case of isothermal, PV is equal to constant. For the ideal gas here, this expression turns out to be this. Okay, so of course this is the analysis based on the relation of the PV here, and one can draw this on a PV diagram. So you have this is isentropic, which essentially means the entropy is constant here, and this is in general polytropic for N less than K, which essentially means here as we decrease your N, your slope decreases for the case of the your path. Okay, and this, if you can remove the heat from the process in such a way that you can maintain the temperature, then this turn out to be isothermal. Okay, and whatever the work here, work is nothing but the area under this PV. This would be the area for particularly isothermal. Okay, that means this particular area covered from here to here in this axis, okay, would be the corresponding work, because that's what you said. P is not a PV integral, it's a VdP integral. Thus it's very clear from this graph or this plot that the area under isothermal curve is the lowest and area under isentropic curve is the most. Okay, so that means the adiabatic compression requires the maximum work. That means this is adiabatic compression, okay, which is your isentropic process, and the isothermal compression is going to be the one which will require the minimum work. Okay, so this is directly based on this plot, and this particular expression comes out to be that. Okay, here of course we have considered that the final limit for all these different conditions P2 and P1 and are same for the different processes which we have discussed here. Okay, so that means the all this diagram, the final pressure at 1 and P and 2 are same. Okay, so based on this exercise for the case of compressor, it is very clear that the work required is going to be a minimum for isothermal process. Okay, so it is valuable to cool intermediately during the process in order to reduce the temperature, and this is something which is clearly evident from our exercise just now. So this is the reason that typically the gas can be compressed in stages, or rather is compressed and cooled between each stages by passing it through a heat exchanger, which we call it intercooler. And the reason is that you reduce the temperature in order to reduce the work required for compressing the gas. So this is an example here. So you have which we are drawing this process on a TS diagram. Initially you are state 1, okay, and you have this polytropic process, you are compressing it, so you are increasing the pressure. At this point you cool this system on the gas at a constant pressure, and then again you pass through again a polytropic process, or you compress it adiabatically again. Okay, so this can be written in terms of this can be drawn on a PV diagram, and which will be evident that you are on a polytropic process as I said, and then you cool at a constant pressure, and then you basically you're bringing the system close to the isothermal condition, and then you again operate on a polytropic process, and thus the overall area would be this. That means this is the amount of the work for the compressor. That means this particular shaded region is the work which you have saved by using a heat exchanger and by employing an intercooling mechanism. Okay. Thus the total work would be, if it is 2 stages, it would be simply the work done in this stage 1, and this is your W compressor 2. Okay. And this can be written in this form. Now the only difference here is that the expressions are same as evaluated in the previous slide. The expressions are same, except for the final pressure for the intermediate would be replaced by Px. Okay. And thus your Px is here, and here will be the Px. The initial condition for the second stage will be Px as well. So Ps becomes the intermediate or the variable here, and you can find out the pressure which will lead to the minimum work here by taking a derivative of this expression and finding out the corresponding pressure. It turns out that when you minimize this compressor work for this 2-stage compression, the results indicate that the ratio of the pressure should be same for both the stages. That means the pressure ratio across each stage of the compressor must be same, and this is the condition which is directly from minimizing this expression. So we have already discussed the kind of work for the reversible case. The turbine we looked at the compressor. We looked at the necessity of intercooling in order to reduce the work required for compressing gas, for example. Now if you want to compare the efficiency of such a device, we look at kind of idealized model. Okay, and this is something which we have already looked into when we discussed the cycles, where we have considered the Carnot cycle, the idealized fictitious kind of cycle, as a theoretical limit. Similarly in this case also, for various flow devices which operates as adiabatic condition, and if we consider such a flow devices, then we will be considering an idealized device where there is no friction and other kind of irreversibility, or thus we can consider a device which is essentially does not have any component of irreversibility, or in other words we can consider an idealized reversible device where your entropy is constant. So most of these devices will be operating in those conditions, and isentropic process will serve as a ideal process for the adiabatic device. Okay, and this is what we are going to take as a kind of theoretical limit. Okay, so in order to find the efficiency of normal turbine, we are going to consider the following. Okay, we will be defining something called isentropic efficiency. On a HS plot, the simple turbine would follow this process in idealized condition. There is going to be a drop in the pressure. So thus your 1 is the initial state, and it undergoes a isentropic process. For the case of a reversible adiabatic case where the entropy is going to be constant, that becomes your idealized model. Okay, and it goes up till 2. S indicates that it is an isentropic process. But for the case of actual process, there will be deviation. So it will deviate from this isentropic path, okay, and it will deviate until it reaches this particular exit pressure. Okay. So naturally the work is going to be different, because as we said, the work is done, and this difference in this change in the enthalpy would be indicative of the work. So to find out the isentropic efficiency of a turbine, we will be making use of this expression, which will be the actual turbine work divided by isentropic turbine work. Okay. So actual would be WA, which will be simply this. Okay, and clearly this work would be less compared to the isentropic one. Okay, this particular efficiency is going to be less than 1. Okay, so we can write this in terms of enthalpy change. So for the case of actual, it will be simply H1 minus H2S would be for your WS, and this is going to be for the actual. Okay, that will be H1 minus H2A. Okay. So that is how we are going to find out the isentropic efficiency of turbine. Similarly, you can also find out the isentropic efficiency for compressor and pump. For the case of a compressor or pump, the initial pressure is going to be low, and along the process, for isentropic process for the idealized where there is no irreversibility, okay, where there is a constant entropy. So we are assuming that the actual and the idealized compressor, the exit pressure is same. So this is your total work for the case of idealized or isentropic process. On the other hand, there will be deviation from the isentropic process for the case of actual process, and thus you need more work to achieve the same change from P1 to P2 state, okay, and thus your actual work is going to be more than Ws. So, in order to have efficiency less than 1, we do not use the same definition as we have used for the case of isentropic efficiency of turbine. Here we are going to use just opposite of that. So, the way we define the isentropic efficiency of compressor is isentropic compressor work, okay, which is going to be smaller than the actual work. So, actual work is in the denominator. So, this makes efficiency less than 1. So, we can write this based on the enthalpy difference here. So, Ws is S2S minus H1 and Wa is S2A minus H1. In this analysis, we are considering the changes in the kinetic energy and potential energies are negligible. Okay. Similarly, for the pump, you can come up with this. Remember that we have already derived that for the gas, VdP term is approximated to dH, and thus you can simply write dH. On the other hand, for the case of liquid, which will be the case for the pump, we are going to simply write VdP integral as simply your V P2 minus P1, and thus the numerator is simply your V P2 minus P1. Okay, so now these are the case for your isentropic processes. Now many times as we already discussed that we take out the heat in order to maintain an isothermal condition. In such case of course you cannot make use of this expression. These expressions were meant for adiabatic reversible case or isentropic case. So you have to make use of a different definition of efficiency for the case of which deviates from adiabatic compressor for the case of isothermal, and thus for the case of isothermal efficiency this will be simply Wt for the ideal isothermal work needed for the operation divided by the actual work. Okay. So, this is how we are going to define for non-adiabatic compressor, or in this case this is isothermal efficiency. We can also extend this analysis for nozzles, which are again an adiabatic device. And for the case of nozzle, which is of course an adiabatic device, these are used to increase the accelerate the fluid, that is increase the velocity. If you assume that inlet velocity is small compared to the exit velocity, okay, then we can simply write the enthalpy balance in this form. Okay. And the way we define the isentropic efficiency of nozzle is simply the actual Ke at the nozzle exit divided by isentropic kinetic energy at the nozzle exit, considering that for actual and as well as for isentropic the initial conditions are same. So, this is how we can depict on a HS plot. So, this is your pressure initial, okay, and the change the final P2 is same for both the actual and isentropic, and the delta H can be simply shown to be in terms of kinetic energy, okay, and thus your change here is simply the kinetic energy for the exit condition at isentropic conditions, and this change for the actual one is going to be simply the kinetic energy at the exit condition for the actual case. So, this is more expressed in this form. So, thus you can write this not necessarily in terms of kinetic energy, but as well as simply the change in enthalpy for the actual case and as well as divided for the isentropic case. Okay. So, that would be the definition of the isentropic efficiency of nozzle, okay, not much different from what we have seen for the case of turbine. Now, you can take an example here. For example, this is a nozzle, you have an inlet condition 950 Kelvin at air, and this is a nozzle. For the case of actual nozzle, the temperature can be higher than compared to the isentropic nozzle due to the irreversibility associated here, and the velocity can be lower than that of an isentropic nozzle. Okay. So, which is of course related to irreversibility associated with actual nozzles. So, you can do this analysis and find out the isentropic efficiency of this flow devices under isotropic conditions. So, with that we will end this particular lecture. In the next lecture we will be applying the entropy balance to various systems. So, I will see you in the next lecture.